Okay, let's begin now. So this slide is visible, suspension type insulator.
Yes, sir.
Previously we started with insulators, and the first type of insulator that we covered was pin type insulator. Then the second type insulator is this suspension type insulator. Let me highlight it. Suspension type insulators. Just go through this. What does it say? I want you guys to go through it. What does it say? I hope you've gone through it. So it says that, let me highlight it. So up to here I'm highlighting. For voltages greater than 33 kV, it's a usual practice to use suspension type insulators. If you remember, pin type insulators we use for voltages up to 33 kV. But it may so happen that we may require voltage applications greater than 33 kV. So when voltage applications greater than 33 kV is required, then we use suspension type insulators. Okay. Then it says they consist of a number of porcelain discs. As we know that ultimately for insulation material, if you want to design an insulator, then the best insulation material to be used is porcelain. So suspension type insulators, it consists of a number of porcelain discs connected in series by metal links in the form of a string. So suspension type insulator is also known as a string insulator. And what happens is that here there is a string, and in the string you have a number of porcelain discs that are connected in series. And those discs are connected to each other by the form of metal links. So suspension type insulators, they consist of a number of porcelain discs. Those are connected in series by metal links, and that forms a string. So it is also known as a string insulator. The conductor is suspended at the bottom end of the string, while the other end of the string is secured to the cross arm of the tower. So as we know that in case of these insulators, one end is secured to the cross arm, and the cross arm is attached to the support. And the job of the cross arm is to provide support to the insulators. And the other end of the insulator, you have conductor. So at the bottom end of the string, you have conductor, and the other end of the string is connected to the cross arm of the tower. Each unit or disc is designed for low voltage, say 11 kV. So inside the suspension type insulator string, you have n number of porcelain discs, and each disc is rated to operate for 11 kV. The number of discs in series would obviously depend upon the working voltage. So if the working voltage is 66 kV, then the 6 discs required to be connected in series on the string. So in a suspension type insulator string, each disc is rated for 11 kV. And definitely it depends, there is this rating depends upon the working voltage. That is, what is the system working voltage, or what is the line voltage? What is the system line voltage that is applied on the conductors? So based on that value, this rating is chosen. So if the line voltage or the system voltage is 66 kV, which is applied on the conductor, then to protect the conductor against the dielectric stress of that voltage of 66 kV, you need to have 6 insulator discs connected in series, where each disc is rated for 11 kV. So 11 into 6 is 66 kV. So ultimately, whatever is the working voltage of the system or line voltage of the system, which is provided on the conductor, that much amount of voltage rating should be there for the insulator discs. So if the working voltage of the system is 66 kV applied on the conductor, that means the insulators should also have a rating of altogether 66 kV. And the insulator string itself is a big insulator. It consists of a number of porcelain discs. Each is rated for 11 kV. So to provide the voltage rating to the insulator of 66 kV, 6 discs which are connected in series should be rated for 11 kV. So 11 plus 11 plus 11 plus 11 plus 11 plus 11 plus 11 will give you total working voltage of 66 kV for the insulators. Because you know that in series connection, voltages add, isn't it? So like if two resistances are connected in series, then the voltages across those two resistances, they add up. Same thing goes for insulator also. Okay, so for example, here you see you have the diagram. Here you have the insulator string. So this is the first porcelain disc. The black one is the metal link, and this metal link is connected at the bottom portion of this first porcelain disc. Below this metal link, again, you have another porcelain disc. Then this porcelain disc at its bottom has got another metal link. And to this metal link, you have the third insulated disc or porcelain disc connected. So altogether, you have 3 porcelain discs which are connected in series. First porcelain disc, second porcelain disc, third porcelain disc. All these are connected in series by the form of metal links. These black portions are the metal links. So these are connected to each other by metal links in the form of a string, and they're connected in series. These 3 porcelain discs. So this altogether forms a string insulator. One end of the string is provided to this curvature that you're seeing. This curvature is the cross arm, and this cross arm is connected to this tower. So here you have this tower, and to this tower or support, whatever you can say, to this tower or to the support, you have the cross arm secured in the curvature form. Then from the cross arm, you have this insulator string, and this insulator string consists of 3 discs. And then at the bottom end of the string, you have this line conductor. You have this line conductor at the bottom end of the string. Okay. So say system voltage or line voltage applied is 33 kV here. You have the line conductor and the system voltage is 33 kV. So 33 kV is applied on the line conductor. So that means if you are applying here insulator string, what should be the voltage rating of the insulator string? That should be also 33 kV, so that it can tackle the dielectric stress of the 33 kV voltage applied on the conductor. Then only conductor will be protected against electric stress or dielectric stress. So insulator string consists of 3 discs here. So each disc is rated for 11 kV. So ये पहला upper disc है उसका 11 kV, plus middle वाला जो disc है उसका 11 kV, plus bottom वाला जो disc है उसका 11 kV. So 11 kV plus 11 kV plus 11 kV, you have 33 kV, the voltage rating for this entire insulator string. There are a few advantages. This is the most common form of insulator that is used in power systems. So there are a few advantages, like number 1, such insulators are cheaper than pin-type insulators for voltages beyond 33 kV. So as we know that pin-type insulators beyond 33 kV, they become uneconomical and bulky. So that is why if the system working voltage is beyond 33 kV, it is better to use suspension type insulators. Second is depending on the working voltage. Depending on the working voltage, the desired number of discs can be connected in series. Like if the working voltage is 66 kV, then you can have 6 discs in series. If the working voltage is say 33 kV, you can have 3 discs in series, because 11 kV is the rated voltage for each disc. So 11 plus 11 plus 11 will give you 33. Similarly, if you have the working voltage as 132 kV, then how many discs will be required in the insulator string? 12 discs, where each disc is rated for 11 kV. 11 kV into 12 will give you 132 kV voltage rating for the insulator string. Then third advantage is this one. If any one disc gets damaged, the whole string does not become useless, because the damaged disc can be replaced by a sound one. So if you have 6 discs in a string and any one disc gets damaged, then the other 5 discs will continue to operate, and that damaged disc can be replaced by a sound one. That is a good one, which is in active format. So the entire string does not become useless. Fourth advantage is the string has more flexibility, because it is a string. Ultimately, it is liable to greater swing, so it will have flexibility. The connection at the cross arm is such that the insulator string is free to swing in any direction and can take up the position where mechanical stresses are minimum. So while you're implementing this insulator string, you don't have to worry about its mechanical stresses, because sometimes when you place the insulators, normal insulators, the arrangement is such that the insulator has to occupy a certain space, certain area, and there the mechanical stresses can be big. But here, as you have a string insulator, so the string insulator, it has got the independence to swing and take up the certain point or certain position where the mechanical stresses will be minimum. So there won't be any mechanical breakdown or mechanical damage for this insulator string. Fifth one, in case of increased demand on the line, I mean to say if suppose the load has increased. If load has increased, then that means the voltage also has to be increased. Okay, so in case of increased demand on the line, the line voltage can be increased to meet up it. In such a case, the number of discs in the string need to be increased to provide sufficient insulation required against the raised voltage. So if you have load raised, if the load value has increased, that means you have to raise the voltage also. So working voltage will increase. And if working voltage increases on the conductor, then the voltage rating of the insulator string also has to be increased. So how can that be increased? By adding more number of discs in series in the insulator string. So suppose you have working voltage of 66 kV. And now the working voltage, so if the working voltage is 66 kV, you have 6 discs connected in series in the form of a string. These are all connected by metal links and they're connected in series to each other. 11 into 6 is 66 kV voltage rating of the insulator string. Now suppose load has increased and the working voltage has to be increased up to say 77 kV. Previously it was 66 kV. Now the working voltage needs to be raised to 77 kV. So one more disc needs to be connected in the string. So instead of 6, previously we had 6 discs in the string. Now you will have 7 discs in the string. So 7 into 11, you will have 77 kV as the voltage rating of the insulator string, which will take care of the working voltage of 66 kV because it is required to provide insulation against the voltage. So this will be sufficient for it. Sixth one is such insulators are provided along with towers. Normally these insulators are best applicable for tower type supports, and already in case of towers we know that there is automatic additional protection provided against lightning. So such insulators are provided along with towers, thereby providing automatic protection against lightning. Then you have strain insulators. Strain insulators, well, whenever there is some kind of tension or pressure developed in the line, then sometimes it becomes important to relieve that tension or to relieve that pressure of the line. So in that case, we use strain insulators. So whenever there is a dead end of the line or there is a corner of sharp curve of the line, it is subjected to a greater tension. In order to release the line of this excessive tension, strain insulators can be used. For low voltage lines that is less than 11 kV, shackle insulators can be used as strain insulators. So whenever, suppose you have a conductor line going from one tower to another tower, and suddenly there is a dead end of the line unexpectedly, or the line has taken a sharp curve. So whenever a sudden dead end is exposed, or whenever there is a sharp curve, there is the conductor line takes a sudden sharp curve, then due to the bending, because ultimately its atomic molecules are facing a little bit of unsimilarities, because it was going in one trajectory. Now the trajectory suddenly changes. So as a result of that, tension builds up. So to relieve the conductors of this tension, you can have strain insulators. Okay, this is just for your syllabus purpose, but the main thing is suspension type insulators. There will be lots of numericals based on suspension type insulator string. Okay, so strain insulators, you can just have an idea about this. We won't go deep into this. It's not required as per the syllabus, just the basic. That is what is the job of a strain insulator. The job of strain insulator is whenever there is tension developed in the line due to any reason, there can be a dead end of the line, or the line takes a sharp curve or sharp corner, then tension is developed. To relieve the tension against to relieve this conductor of this tension, we can use strain insulators. This is how it looks like. Suppose here you have a pole, and on the pole you have the cross arm, and to the cross arm you have strain insulator. So strain insulator is placed, as you can see, like horizontally, and it looks like your suspension type insulator string only. That is here. Here you will have a cross arm on the pole. Then to the cross arm on the pole, the first this disc insulator is connected. Then there is a metal ring or metal link at the bottom end of the first disc. Then below this metal link, you will have another porcelain disc. So here you have 2 porcelain discs that are connected in series to each other by the form of metal links in the form of a string. But these are placed horizontally. Okay. Previously in suspension type insulator, you saw that they were placed vertically. Here they are placed horizontally, and at the bottom end of the string, you will have the conductor. So this arrangement ensures that the tension which is developed on the conductor slightly reduces. And ultimately, you will have shackle insulators. This is also just for just to know, that is just a basic idea of shackle insulators. One marks or 2 marks question may come. No need to go deep into it. In the early days, shackle insulators were used as strain insulators. So previously, a few years back, in order to ensure that the line is relieved from excessive tension or stress or pressure, shackle insulators were used as strain insulators. They look like strain insulators only, but nowadays they are used for low voltage distribution lines only. Such insulators can be used either in a horizontal position or in a vertical position. So shackle insulators, these are used for low voltage distribution lines, but ultimately these are nothing but your suspension type insulators only. And these can be placed either horizontally, like your strain insulators, to relieve the line of excessive tension, or they can be placed in a vertical position so that they can, they can perform like your suspension type insulators. But the main suspension type insulators, they are mainly used for transmission purposes, for handling high voltages, whereas the shackle insulators, these are mainly used for handling low voltages, especially at the distribution end. Okay. So do not expect that too many number of discs will be connected or used in shackle insulators. Do not expect that. In case of pure suspension type insulator, you can expect that. Okay, then there comes this little bit of theory that comes here. It is written as, please, it is written in my, it was written in a very fast format by my hand. Yeah, I wrote it in very quick time. So I will just give dictation so that you can follow it. Topic name is potential distribution. Potential distribution over suspension insulator string. So now a derivation will come, some concepts will come with respect to your suspension type insulator string. So the topic name is potential distribution over suspension insulator string. What is written here? A string of suspension insulators consists of a number. A string of suspension insulators consists of a number of porcelain discs connected in series through metal links that we already know that in a suspension insulator string, we'll have a number of porcelain discs that are connected in series via metal links. Figure 1 shows 3-disc string. So figure 1 will come where you will have a string insulator and there you will have 3 porcelain discs. Okay, so figure 1 shows 3-disc string of suspension insulators. The porcelain portion of each disc is in between 2 metal links, because ultimately these discs are connected to each other via metal links only. So automatically the porcelain portion of each disc will come in between 2 metal links. Therefore, each disc forms a capacitor C as shown in figure 2. So here if you go, wait a second. So this is figure 1. At the top, you have your tower. Please follow the cursor, my mouse pointer. At the top, you have the tower. टावर के नीचे से यहाँ पे क्रॉस आर्म दिखाने का जरूरत है नहीं, क्योंकि क्रॉस आर्म का इफेक्ट इन द न्यूमेरिकल्स इज नेग्लेक्टेड आउट. ठीक है, टावर है एकदम टॉप एंड पे. ये टावर से कनेक्टेड है मेरा ये पहला जो है पोर्सिलेन डिस्क. ठीक है, ये पोर्सिलेन डिस्क के यहाँ पे क्या है, मेटल लिंक. ठीक है, ये जो डॉटेड ब्लैक डॉट जो देख रहे हो वो है मेटल लिंक. इस मेटल लिंक के बाद में क्या आ रहा है, एक और पोर्सिलेन डिस्क. फिर इस पोर्सिलेन डिस्क के नीचे क्या है, एक और मेटल लिंक. फिर इस मेटल लिंक के नीचे क्या है, एक और पोर्सिलेन डिस्क. उसके नीचे एक और मेटल लिंक एंड बॉटम एंड में है कंडक्टर. अगर याद करो इंसुलेटर स्ट्रिंग में क्या रहता है, इंसुलेटर स्ट्रिंग में वन एंड ऑफ द स्ट्रिंग इज सिक्योर्ड टू द क्रॉस आर्म ऑन द टावर. तो यहाँ पे क्रॉस आर्म दिखाने का जरूरत है नहीं. डायरेक्टली यू कैन से दैट वन एंड ऑफ द स्ट्रिंग इज कनेक्टेड टू द टावर एंड द अदर एंड ऑफ द स्ट्रिंग देयर इज बॉटम एंड ऑफ द स्ट्रिंग. वहां पे क्या रहता है, कंडक्टर रहता है. सो बॉटम एंड ऑफ द स्ट्रिंग इज कनेक्टेड टू द कंडक्टर. सो टावर से निकल रहा है पहला पोर्सिलेन डिस्क. पोर्सिलेन डिस्क के नीचे जो ब्लैक पोर्शन है वो है मेटल लिंक. इस मेटल लिंक के थ्रू इसके नीचे एक और पोर्सिलेन डिस्क कनेक्ट किया जाता है. देन इस पोर्सिलेन डिस्क के नीचे आता है एक और मेटल लिंक. देन इसके थ्रू उसके नीचे एक और पोर्सिलेन डिस्क कनेक्ट किया जाता है. एंड ऑटोमेटिकली यहाँ पे भी सपोज एक तुम्हारा मेटल लिंक है एंड इसके नीचे कंडक्टर. ओके, नाउ टावर इज यूजुअली कनेक्टेड टू ग्राउंड आल्सो, वी नो. सो एनीवेज, now insulator capacitor also acts as insulator, we know. And porcelain disc also acts as insulator. So that's why here each porcelain disc is basically replaced or represented by equivalent capacitance. So पहला जो porcelain disc है उसके बदले में हम लोग यहाँ पे शो कर रहे हैं कैपेसिटेंस. ठीक है, उसके नीचे एक और है, ये जो सेकंड पोर्सिलेन डिस्क है, दैट सेकंड पोर्सिलेन डिस्क इज आल्सो रिप्लेस्ड बाय कैपेसिटेंस. third porcelain disc जो है that is also replaced by capacitance. So instead of drawing these 3 porcelain discs, you can draw 3 capacitances which are in series with respect to each other. These are mutual capacitances. Okay, and between each capacitance you have your metal links. All right, and porcelain disc is replaced by mutual capacitance because mutual capacitance acts as insulator. Porcelain disc also acts as insulator. So that's why porcelain disc is getting replaced by this mutual capacitance C. And normally these values are equal to each other. This C, AC, these are all equal to each other, mutual capacitances. But the problem जो होता है वो है कि ये है तुम्हारा टावर, एकदम टॉप पोर्शन पे है टावर. और एक चीज देखो फिगर 2 में, the same current I flows through all these capacitances. ये जो करंट I है, same current I flows through all these capacitances. ठीक है, तो यहाँ पे है मेरा टावर इज कनेक्टेड टू ग्राउंड. टावर इज कनेक्टेड टू ग्राउंड. अभी प्रॉब्लम जो देखा जाता है वो है कि वाया एयर मीडियम ऑल्सो कैपेसिटेंस कैन एग्जिस्ट. सो हाउ दैट एग्जिस्ट ना, ये जो मेटल लिंक है, हर एक मेटल लिंक से वाया एयर एक शंट कैपेसिटेंस निकलता है जिसको बोला जाता है C1, एंड दैट इज ऑलवेज कनेक्टेड टू द ग्राउंडेड पोर्शन ऑफ द टावर. सो ये जो C1 है इसको बोला जाता है शंट कैपेसिटेंस दैट एग्जिस्ट बिटवीन दिस मेटल लिंक एंड द ग्राउंडेड टावर. सिमिलरली यहाँ पे भी एक मेटल लिंक है, इस मेटल लिंक से भी एक शंट कैपेसिटेंस निकलता है C1 which is connected to the grounded tower. And similarly at the bottom end of the string, जहाँ पे मेरा bottom portion मतलब एकदम end में जो मेटल लिंक है वहां से भी एक शंट कैपेसिटेंस निकलता है C1 which is connected to the grounded tower. So प्रॉब्लम क्या होता है ना, फिगर 2 में अगर देखो, इन फिगर 2 सेम करंट I was flowing through all these capacitances. ठीक है, तो हर एक जो यहाँ पे भी कैपेसिटेंस है C, यहाँ पे भी कैपेसिटेंस है C, यहाँ पे भी कैपेसिटेंस है C. सेम करंट I इसके थ्रू भी फ्लो कर रहा है, C के थ्रू, ये C के भी थ्रू फ्लो कर रहा है, ये C के भी थ्रू फ्लो कर रहा है. तो अल्टीमेटली इनके अक्रॉस में जो वोल्टेज डिस्ट्रीब्यूशन होगा वो क्या होगा, यूनिफॉर्म, मतलब इक्वल. सो अगर टोटल लाइन वोल्टेज है मेरा V, देन टोटल इंसुलेटर का भी वोल्टेज क्या होना चाहिए, V. इसका मतलब ये जो कैपेसिटेंस है इसके अक्रॉस में वोल्टेज होना चाहिए V/3. ये कैपेसिटेंस जो है उसको अक्रॉस वोल्टेज होना चाहिए V/3. ये जो कैपेसिटेंस है उसके अक्रॉस भी वोल्टेज होना चाहिए V/3. सो दिस 3 कैपेसिटेंसेस आर कनेक्टेड इन सीरीज. इसका मतलब इन तीनों का वोल्टेजेस भी ऐड होंगे. तो ये कैपेसिटेंस का जो वोल्टेज है V/3 will be added with this capacitance voltage, that is V/3. Then that will be added to the voltage across this capacitance, that is V/3. So ये जो कैपेसिटेंस के अक्रॉस वोल्टेज मिला V/3, ये कैपेसिटेंस के अक्रॉस जो वोल्टेज मिला V/3, ये कैपेसिटेंस के अक्रॉस जो वोल्टेज मिला V/3, as the capacitances are in series, so their voltages add up. So V/3 plus V/3 plus V/3 shall form your V, and this V will be again the voltage rating of the insulator string. And ये वोल्टेज मेजर किया जाता है across the capacitances. So पहला जो V/3 is measured between tower and the metal link, because tower is also made up of ultimately metal only. ठीक है, so पहला जो वोल्टेज है V/3 is measured between the tower and this first or the topmost metal link. In between this you have capacitance C. So V/3 is the voltage of this mutual capacitance C, topmost. Then जो middle वाला mutual capacitance है C, उसके across में भी क्या है, वोल्टेज V/3. ये वोल्टेज कहाँ से कहाँ मेजर किया जाएगा ना, ये जो टॉप मोस्ट मेटल लिंक है यहाँ से शुरू होके ये जो मिडिल मेटल लिंक है, मिडिल मोस्ट मेटल लिंक, यहाँ तक इसको मेजर किया जाता है. एंड ये टॉप मोस्ट मेटल लिंक और मिडिल मोस्ट मेटल लिंक दोनों के बीच में क्या है, तुम्हारा सेकंड जो कैपेसिटेंस है, देयर इज म्यूचुअल कैपेसिटेंस. म्यूचुअल कैपेसिटेंस जो है C, वो है. ठीक है, एंड देन सिमिलरली ये जो मिडिल वाला लिंक है एंड जो बॉटम वाला मेटल लिंक है, मिडिल वाला मेटल लिंक एंड बॉटम वाला मेटल लिंक जो है, इन दोनों के बीच में भी वोल्टेज को मेजर किया जाता है, which comes out to V/3, which is the voltage across this bottom most mutual capacitance C. बट जो प्रॉब्लम होता है वो है कि बेसिकली ये जो शंट कैपेसिटेंस अभी देख रहे हो, इफ यू गो टू फिगर 3 में क्या है, नाउ यू हैव शंट कैपेसिटेंसेस C1 which is connected between the first metal link or topmost metal link and the grounded tower. Then another C1 you have that is connected between this second metal link and the grounded tower, and another shunt capacitance C1 you have which is connected between this bottommost metal link and the grounded tower. तो इसके कारण क्या होता है ना, करंट इन लोग के थ्रू भी डिस्ट्रीब्यूट कर जाएगा. तो ये जो करंट I कंडक्टर से निकल रहा था, ये करंट I कंडक्टर से निकल के जैसे ही ये पहला मेटल, ये जो बॉटम मोस्ट मेटल लिंक पे आया, देन कुछ पोर्शन उसका ऊपर चला जाएगा, दैट इज एज I3, कैपिटल I3, एंड जो बाकी पोर्शन है करंट आई का ऑफ द कंडक्टर वो फ्लो करेगा ये C1 के थ्रू, दैट इज बॉटम मोस्ट जो मेरा शंट कैपेसिटेंस C1 उसके थ्रू. सो लेट दैट बी स्मॉल I3. सो क्या हुआ ना, कंडक्टर से मेन करंट क्या निकला मेरा I, कैपिटल I, वो मेटल लिंक तक गया. Kirchhoff's law, as per Kirchhoff's law, we know that whenever current comes down to a node and the node has got certain paths emanating from it, then the current gets distributed or divided in those paths. तो इस नोड से कितना पाथ्स निकल रहा है, एक ये वाला पाथ एंड एक ये वाला पाथ. ठीक है, ये जो मेटल लिंक है बॉटम मोस्ट मेटल लिंक, तो बॉटम मोस्ट मेटल लिंक के बाद में देयर आर टू पाथ्स, दिस पाथ व्हिच गोज थ्रू द बॉटम मोस्ट सेल्फ कैपेसिटेंस, बॉटम मोस्ट म्यूचुअल कैपेसिटेंस C, एंड एक दूसरा पाथ जो कि जा रहा है ये बॉटम मोस्ट C1 के थ्रू, दैट इज बॉटम मोस्ट शंट कैपेसिटेंस. सो जो बॉटम मोस्ट जो सेल्फ कैपेसिटेंस या म्यूचुअल कैपेसिटेंस है कैपिटल C, उसके थ्रू करंट जा रहा है कैपिटल I3, एंड ये जो बॉटम मोस्ट शंट कैपेसिटेंस C1 उसके थ्रू करंट जा रहा है स्मॉल I3. सो कंडक्टर से जो मेन करंट I निकला दैट इज इक्वल्स टू कैपिटल I3 प्लस स्मॉल I3. देन ये कैपिटल I3 जब ये जो मिडिल वाला मेटल लिंक है यहाँ पे जब आया, then middle wala metal link se bhi how many paths are emanating? Two paths. One is this path which is going up through the middle capacitance, that is through the middle capacitance C, uske through ja raha hai current I2, capital I2, and दूसरा path किसके through जा रहा है, this middle वाला C1 जो है means middle वाला shunt capacitance उसके through जा रहा है, तो उसके through current क्या जा रहा है, suppose से small I2. So capital I3 is equals to capital I2 plus small I2, because Kirchhoff's current law हम लोग को बोलता है summation of outgoing currents equals to summation of incoming currents. So ये जो middle वाला जो metal link है यहाँ पे incoming current मेरा क्या है I3 only. So summation of incoming current is equals to summation of outgoing currents. इस node से क्या क्या currents निकल रहा है, एक है capital I2, एक है small I2. So capital I3 will be equals to capital I2 plus small I2. Then capital I2 comes to this topmost metal link. After coming down to this topmost metal link, again you have two more paths. You have two paths emanating from the topmost metal link. One path is this that goes through C, capital C, that is your self capacitance or mutual capacitance, and दूसरा वाला क्या है, दूसरा वाला है through the shunt capacitance C1. So इसका मतलब C के थ्रू एक करंट जाएगा, उसको ले रहे हैं कैपिटल I1, और C1 के थ्रू एक करंट जाएगा, उसको ले रहे हैं हम लोग स्मॉल I1. ठीक है, so capital I2 will be equals to capital I1 plus small I1. So now you see, previously we had the same current I through all these capacitances, that is through all these mutual or self capacitances. But now through this topmost C, you have current I1, capital I1. Through this middlemost C, you have current I2, that is a capital I2. Through this bottommost C, you have current I3, that is capital I3. Okay. As a result, I1, I2, and I3 are not equal to each other. Why? Because you have these currents, leakage currents, small I1, small I2, small I3, which are flowing through this C1, C1, and C1. So current distribution is not uniform. As a result, voltage distribution will also not be uniform. So topmost capacitance C जो है उसके across में है voltage V1, middlemost capacitance जो है उसके across में voltage है V2, bottommost capacitance जो है उसके across में voltage है V3. V1 plus V2 plus V3 will give me the total voltage for this entire insulator string. So that's what is written here. मैं एक बार डिक्टेट कर दे रहा हूँ, कहाँ तक बोला था मैं, फिगर 2 तक बोला था. Therefore each disk forms a capacitor C as shown in figure 2. एक बार फिर से कर रहा हूँ पहले से. A string of suspension insulators consists of a number of porcelain disks connected in series through metallic links. Figure 1 shows 3 disk string of suspension insulators. Figure 1 में हम लोग देखा suspension insulator string था, वहाँ पे कितना डिस्क था, 3 डिस्क था. The porcelain portion of each disk is in between two metal links. तो वो हम लोग डायग्राम में देखे कि basically each disk it basically lied between the two metal links. Each disk, the porcelain portion of each disk. Therefore, each disk forms a capacitor C as shown in figure 2. It's known as mutual capacitance or self capacitance. If there were mutual capacitance alone, अगर मतलब mutual capacitance या फिर self capacitance मतलब क्या है, वो जो capital C था वो वाला. So if those capacitances were alone, there is mutual capacitance were alone, then charging current would have been the same through all the disks, and consequently voltage across each unit would have been the same, that is V by 3 as shown in figure 2. Figure 2 में कोई shunt capacitance नहीं था, only mutual capacitance था, and all the mutual capacitances के through same current जा रहा था, charging current, because small amount of charging current will always flow through the capacitances, that will always be there. ठीक है, उसके वजह से ही वोल्टेज बिल्डअप भी होता है उसके अक्रॉस, सो दैट इज रिक्वायर्ड दैट चार्जिंग करंट, स्मॉल अमाउंट ऑफ। सो बेसिकली बोल रहा है कि फिगर 2 में अगर सिर्फ म्यूचुअल कैपेसिटेंस रहता, शंट कैपेसिटेंस नहीं रहता, देन वोल्टेज डिस्ट्रीब्यूशन मेरा यूनिफॉर्म होता है। दैट इज हर एक डिस्क के अक्रॉस में या फिर हर एक म्यूचुअल कैपेसिटेंस कैपिटल सी के अक्रॉस में वोल्टेज डिस्ट्रीब्यूशन सेम रहता, V/3 V/3 V/3, तीनों को ऐड कर लेते हैं, टोटल वोल्टेज ऑफ द स्ट्रिंग मिल जाता, दैट वाज V, provided that shunt capacitance was not there. But in reality, shunt capacitance is there, as you can see in figure 3, isn't it? So that's why, however, in practice, capacitance also exists between metal fitting of each disc and tower of earth. But shunt capacitance भी exist करता है, वो हम लोग देखे, it exists between each metal fitting and it exists between each metal fitting and the grounded tower. This is known as shunt capacitance C1. ठीक है? Due to C1, charging current is not the same through all the discs of the string. तो अल्टीमेटली हम लोग क्या देखें कि बेसिकली जैसे शंट कैपेसिटेंस भी इक्वेशन में आ गया, करंट डिस्ट्रीब्यूशन नो लॉन्गर रिमेन्स यूनिफॉर्म, डिफरेंट करंट्स यू विल हैव थ्रू डिफरेंट म्यूचुअल कैपेसिटेंसेस, ठीक है। एज अ रिजल्ट वोल्टेज डिस्ट्रीब्यूशन विल नॉट बी आल्सो यूनिफॉर्म, you will have V1 voltage across mutual capacitance C, you will have V2 voltage across C, you will have V3 voltage across the bottommost C, V1, V2, V3 are not equal to each other, ठीक है। ये किसके वजह से हुआ? शंट कैपेसिटेंस की वजह से हुआ, ऑल दोस 3 C1s की वजह से हुआ, क्योंकि उसके थ्रू भी कुछ अमाउंट ऑफ करंट जाना शुरू किया, तो उस वजह से करंट डिस्ट्रीब्यूशन it is not uniform, so voltage distribution will not be uniform. So due to C1 comma देके charging current is not the same through all the discs of the string, therefore voltage across each disc will be different, V1, V2, V3. The disc nearest to the line conductor will have the maximum voltage. तो हम लोग फिगर 3 में देखे थे कि बेसिकली जो बॉटम मोस्ट डिस्क था, मतलब बॉटम मोस्ट जो सी था, इट वाज कनेक्टेड नियरेस्ट टू द कंडक्टर, कंडक्टर के ऊपर जो पूरा सिस्टम वर्किंग वोल्टेज आ रहा है तो वो पूरा का पूरा सिस्टम वर्किंग वोल्टेज के नियर में क्या है ना, बॉटम मोस्ट इंसुलेटर था मेरा सी, तो उसके ऊपर बहुत प्रेशर आएगा, लेकिन जैसे जैसे ऊपर जाएंगे वोल्टेज प्रेशर कम होता जाएगा, because charging current through the string of the string has the same value of the disc nearest to the conductor. मतलब ये टॉप मोस्ट है C, इसके अक्रॉस है वोल्टेज V1, मिडिल मोस्ट क्या है मेरा C, उसके अक्रॉस वोल्टेज है V2, बॉटम मोस्ट क्या है मेरा ये वाला C, उसके अक्रॉस वोल्टेज है V3। ना जो बॉटम मोस्ट C है मेरा म्यूचुअल कैपेसिटेंस या फिर पोर्सलिन डिस्क, इट इज कनेक्टेड नियरेस्ट टू द कंडक्टर, this black dotted portion, big black dotted circle hazy portion is my conductor, and bottommost जो capacitance है, self capacitance या mutual capacitance, it is connected nearest to this conductor. तो इसके across में जो voltage आएगा, that is ये जो bottommost capacitance है, इसके across जो voltage आएगा वो भी होगा highest. then जैसे जैसे ऊपर जाएंगे voltage थोड़ा घटते जाएगा, so जो bottommost insulator है ये हमेशा बहुत pressure में रहेगा अगर ऐसा scenario आया तो, ठीक है। So some important points to remember are points. Number 1, the voltage impressed on a string of suspension insulators does not distribute itself uniformly across the individual discs due to the presence of shunt capacitance. As because shunt capacitance is there, the voltage which is obtained across the string insulator is not uniform, is not uniformly distributed or divided. सेकेंड पॉइंट क्या है? सेकेंड पॉइंट है द डिस्क नियरेस्ट टू द कंडक्टर, मतलब बॉटम मोस्ट जो डिस्क है मेरा, ये बॉटम मोस्ट सी जो है म्यूचुअल कैपेसिटेंस या फिर सेल्फ कैपेसिटेंस, द डिस्क नियरेस्ट टू द कंडक्टर हैज मैक्सिमम वोल्टेज अक्रॉस इट, बिकॉज एक तो है कि जो बॉटम मोस्ट सी है या बॉटम मोस्ट इंसुलेटर या बॉटम मोस्ट डिस्क इज कनेक्टेड नियरेस्ट टू द कंडक्टर, ऊपर से वोल्टेज डिस्ट्रीब्यूशन इज नॉट यूनिफॉर्म, नॉट द सेम ऑल थ्रू आउट, तो ऑटोमेटिकली यहाँ पे हाईएस्ट वोल्टेज अपीयर करेगा अक्रॉस दिस डिस्क। As we move towards the cross arm, मतलब जैसे जैसे we move up towards the tower through this insulator string, voltages across the discs, they are in decreasing format. So as we move towards the cross arm, voltage across each disc goes on decreasing. लेकिन ये प्रॉब्लम अराइज नहीं करता अगर शंट कैपेसिटेंस नहीं रहते, तो यहाँ टोटल जो वोल्टेज होता है वो इक्वली डिवाइड हो जाता है तीनों के बीच, बट इन रियलिटी इट इज नॉट पॉसिबल लाइक दैट। Third point is the unit nearest to the conductor is under maximum electrical stress, and is likely to be punctured. So जो bottommost disk या bottommost self capacitance mutual capacitance देखे, इसमें बहुत chance है to get punctured because ये बहुत ज़्यादा maximum stress में तो यही है ना, क्योंकि जो maximum voltage होना चाहिए, जो total voltage होना चाहिए, उसका maximum portion वो अकेला ले रहा है, so it can get punctured because वो उसको rating को increase कर जा रहा है, exceeding its rating. उसका भी तो capacity है लेने का, लेकिन उसको capacity को exceed करके अगर voltage उसको impress किया जाएगा continuously, destroy हो जाएगा. Therefore, means must be provided. Therefore, means must be provided to equalize the potential across each unit. So, इसलिए there should be some ways through which you should be able to equalize the potential distribution across the string insulator. Fourth one is if the voltage impressed across the string were DC. ये तो AC voltage देख रहे थे. अभी अगर suppose string के ऊपर जो voltage apply किया जा रहा है, impress किया जा रहा है, वो अगर DC voltage होता, then ये प्रॉब्लम हम लोग के लिए एग्जिस्ट ही नहीं करता शंट कैपेसिटेंस होते हुए भी. क्यों? बिकॉज देन वोल्टेज अक्रॉस ईच यूनिट वुड बी सेम. इट्स बिकॉज इंसुलेटर कैपेसिटेंसेस आर इनइफेक्टिव फॉर डीसी. ठीक है, सो डीसी का कोई इफेक्ट नहीं रहता, मतलब डीसी यहाँ पे एसी सिस्टम जो है उसके वजह से, लेकिन अल्टीमेटली या डीसी डिस्ट्रीब्यूशन अगर रहता देन पोटेंशियल डिस्ट्रीब्यूशन इससे बेहतर रहता है, एटलीस्ट नियर बाय वेरी इक्वल टू तो रहता है एटलीस्ट, because these are ineffective in case of DC supply. Then एक formula आता है, उसको बोला था string efficiency. इसको देख लो, the ratio of voltage across the whole string. So the ratio of the voltage across the whole string to the product of the number of disks and the voltage across the disk nearest to the conductor is known as string efficiency. Very, very common and a very, very important formula, I would say, string efficiency. इसको ऊपर depend करके बहुत सारे numericals है that we have to see. So string efficiency is nothing but it's a ratio between numerator में क्या है, voltage across the entire string to that of, मतलब नीचे में n मतलब number of disks into voltage across the disk nearest to the conductor. So this formula you have to remember. We have to calculate string efficiency. इसका relevance क्या है ना, higher the string efficiency, more uniform will be the voltage distribution. String efficiency जितना high होगा, मेरा voltage distribution भी उतना uniform होगा. ये हम numericals में देखेंगे जब numericals को touch करेंगे, ठीक है? So today up to this only, guys. I will just take your attendance. Okay, guys. Thank you then. In the next class, I shall start from the next topic.
Thank you, sir.
And thank you, sir.